passive filters gave us the four basic shapes: low pass, high pass, band pass, and band reject. But passive filters cannot create voltage gain, and the response can change when the next stage loads them. Active filters add an op-amp so the frequency selection and the signal gain can be designed more deliberately. The op-amp does three useful jobs. First, it can isolate one stage from the next. Second, it can provide voltage gain, so the passband does not have to be below unity. Third, it lets us build clean first-order filter blocks using resistors and capacitors instead of inductors. Start with an inverting active low-pass filter. The input resistor feeds the inverting node. In the feedback path, a resistor is placed in parallel with a capacitor. At low frequency, the capacitor is almost open, so the feedback is mostly through the resistor. At high frequency, the capacitor reduces the feedback impedance, so the closed-loop gain falls. For this low-pass form, the passband gain is set by the resistor ratio minus Rf over Rn. The cutoff comes from the feedback time constant Rf times C. So the angular cutoff is 1 over Rfc and the Hertz cutoff is 1 over 2 pi Rfc. The active high-pass version moves the capacitor into the input path. At low frequency, the input capacitor blocks the signal, so the output is small. At high frequency, the capacitor behaves almost like a short, and the circuit becomes an ordinary inverting amplifier. For the high-pass form, the high-frequency gain is again minus Rf over Rn. The cutoff now comes from the input time constant Rn times C. Below cutoff, the input path is weak. Above cutoff, the input reaches the inverting node efficiently. The magnitude curves look familiar, but there is one important difference from passive RC filters. The flat part of the curve can sit at a chosen gain, not just at 0 decibels. The op-amp gives us a design handle for gain, while the resistor-capacitor product gives us the corner frequency. A quick design example. For an active low-pass cutoff of 1 kHz, choose C equal to 10 nanofarads. Then RF is about 15.9 kiloohms. If you want a passband gain of -2, choose Rn about half of RF. The same workflow works for high-pass filters, but the cutoff resistor is the input resistor. Active filters are not magic. The op-amp must have enough gain bandwidth at the frequencies you care about. Large fast signals can hit the slew rate limit. The output cannot exceed the supply rails, and real resistor and capacitor tolerances shift the cutoff from the ideal value. The design recipe is simple. Choose the filter shape, choose the cutoff frequency, pick a convenient capacitor. Compute the resistor that sets the time constant, then choose the resistor ratio that sets passband gain. Finally, check the op-amp datasheet against bandwidth, slew rate, signal swing, and load. Summary: an active low-pass or high-pass filter combines a first-order RC frequency response with op-amp gain and buffering. Low-pass puts the capacitor in the feedback path. High-pass puts the capacitor in the input path. Next, we will use the same active filter idea to build middle band behavior, active band pass and band reject filters.